Okay, this is 8.2.1, looking at the equilibrium constant K and the relationship with that and balanced reactions. So equilibrium constant, you're going to find the history of it, how it developed, used balanced reactions to write equilibrium expressions, and vice versa, and when to include water in the equilibrium expression. So equilibrium law, this is actually the old textbook, I hadn't realized. So what they did originally to develop this mathematical way of looking at an equilibrium is that they thought that obviously you start with a certain concentration of reactants and you're going to end up with a certain concentration of products. So depending on how much you've got, there must be some mathematical way of knowing how much product you're going to make depending on the amount of reactant. So they did a whole lot of different equilibrium mixtures with different concentrations to see if they could find a pattern, a mathematical way of expressing. So they thought that it would be some sort of fraction, that this is a fraction of what you have here. So the equilibrium constant, the fraction that we're looking at, is dependent on temperature. So it changes, this value changes if the temperature changes. So we always have to quote temperature. So when you look at these numbers, it doesn't seem to be an obvious pattern. The only thing that you notice is that even however much reactants you've got, the amount of product that you make is a very small amount. So the reaction doesn't go very far to the right before the rate starts to become equal. All right, so first thing, they tried a straightforward fraction. They made the products over the reactants, set up and had a look, and didn't find a pattern. So then some mathematical person must have realized that there was a relationship between the mole ratio concentration. So they put the concentrations to the power of your mole ratio amounts, set up a fraction again, and found that the number was consistent. There was a pattern. Okay, so the relationship that they used is between the mole ratios and the concentration. So this ratio, this fraction, is called the equilibrium constant. The fraction number is the equilibrium constant, and it's temperature dependent. So it's a fraction where the products are on the top, but the reactants are on the bottom. You need to remind yourself of this so that you do not get this incorrect. We don't use C concentration of. To make it faster to write, they use square brackets instead of C normal brackets concentration. They use square brackets to represent concentration. So whatever the products are, to the power of whatever their mole ratio amounts, multiplied and divided by the same thing. Okay, so the difference between, I've just added this slide, the difference between the equilibrium expression and the equilibrium constant is the whole setup, the whole thing is called the equilibrium expression. So if you're asked to write an equilibrium expression, then you just write the whole thing. If you're asked to find the equilibrium constant, then you need to multiply and divide and end up with a number for equilibrium constant. So it's a calculation. So K is the equilibrium constant and the whole thing is the equilibrium expression. So write a balanced equation for this for the reaction which has this equilibrium expression. Okay, so pause it, have a go. We did this in class, see if you can remember how to do it. Remember that it's an equilibrium. So on the exam, you would lose marks when you're writing this reaction if you did an arrow going in the forward reaction only, rather than an equilibrium arrow forward and back. You can be forgiven sometimes if you write one of these equilibrium direction arrows for a reaction that only goes to the right and finishes. So to write one is sometimes better than to just do normal arrows all the time. All right. These are in the same state. The gas these are all gases, this particular reaction. So we've got our products, and the 2 is a mole ratio number, and your reactant. So can you pause this and have a go at that one? Write the expression, the whole expression for this reaction. Okay, so products squared and reactants. Remember your square brackets. So if you haven't got your square brackets, just note down that you forgot to put them. Write an equilibrium expression for a reaction in a solution with water as the reactant or product. So if the previous reaction that we did had gases, all gases, if you have all a solution where it's in aqueous solution, then the main chemical is water. So if you're producing water or your reactant was water, then because there's so much water, you can talk about the concentration of water as how many moles of water there is in a litre, which is really density. But because there's so much, if you added a little bit more, you really haven't changed the number of moles of water, or if you remove some, you really haven't removed some. So the water concentration number is included in this number permanently, and so you don't write it in the expression. This is not the same if water was a product, if you do a reaction with gases and water is produced, or if you need water in a reaction with gases, then obviously it's not the same. You've only got a little bit of water. So just be careful when you're writing water. So this is an example of that. We've got this aqueous reaction, and one of the products is water. So because you're making, 6 molecules of water in however many billion molecules of water, you can just leave that off the expression. So because you've left that number has not been totally lost, the concentration of water, it's been permanently included in this number. So because this number has kind of been fiddled with, we write this little symbol down the bottom to say equilibrium constant for concentration. And we used to do weak acids and things, in which case we would have written acid or base down there, but we're not doing, this is the only one, and we thought we weren't doing these kind of things anymore, and then it popped up in the exam. So for water, and same thing for solids, clearly you can't have a concentration of solids, so in that case you just leave it off.